All right, guys. Sorry I couldn't be there today, but I'm going to go over your homework with you. The first homework problem you had to do was problem 10 from your worksheet packet. Here's a picture of it. I'm going to switch over to a PowerPoint slide so I can work it out for you. So let's draw the picture real quick. We had two ropes, and those two ropes are supporting a weight. So the picture might look something like this. We had an imaginary line drawn down the middle. This was angle theta, and so is this. And we want to know what is the tension in each rope. Here's what we're going to do. We're first going to break, think about it this way. The weight of this rope, the vertical weight, is supported half by this rope and half by this rope. But we're going to take the tension in that rope and break it down into a vertical component and a horizontal component. Where this vertical component of each rope is equal to half the weight. The vertical component of each rope has to support half the weight. So we know an angle and we know a side. This is the side of the triangle we're trying to find. That's the tension. That's the total force in the rope. So to calculate that, we're going to use cosine. We're going to say cosine of theta is equal to the adjacent side, which is W over 2, all over the hypotenuse. So if we solve that out for x, we can say x is equal to W over 2 divided by cosine theta do a little bit of math on that. That's going to end up simplifying to be x equals W over 2 cosine theta. And that's our answer. That's the total tension in the rope, the total force exerted in that rope. That's taking into account both the horizontal and the vertical components. Now let's look at the second problem. Your second homework problem was number 11. Here's number 11. The ball falls straight down through the air under the influence of gravity. There's a retarding force on the ball with a magnitude of F equals BV, where V is the speed of the ball and B is a positive constant. The magnitude of the acceleration A of the ball at any time is equal to which of the following? Here's the thing. Let's go to PowerPoint again for this one. What this is saying is that you've got a ball that's falling. And it's saying that it's falling down, but there's a force that's acting, retarding the force. That means it's slowing it down. That retarding force is acting up. And that force has to be what we call air drag or air resistance. And the air drag force is equal to B times V. The force that's pushing the ball down is its weight, or mg. So if we can calculate a net force, we can say that the net force is equal to the weight, mg, minus the drag. That's not what we're looking for. What we're looking for in this problem is the acceleration. And we know that the acceleration is equal to Newton's second law says acceleration is equal to F net divided by mass. So let's take the net force that we calculated up here, mg minus vv, and let's divide that by the mass. Now if you look at your answer choices on your sheet, that's not one of them. But if we divide both these terms by mass, we could write this way, g minus vv over m. And if you look a little bit more closely, that is answer choice B. So your answer on number 11 is B, g minus bv all over m. Going forward now to problem 14. All right, so here's problem 14. You've got a mass on an incline. A plane 5 meters in length is inclined at 37 degrees as shown above. A block of 20 newtons is placed at the top of the plane and allowed to slide down. You want to find the mass of the block, and you also want to find the magnitude of the normal force exerted on the block by the plane. Again, let's go to a PowerPoint. Draw it back out real fast. We've got a plane. We've got a box sitting on that plane. It's a 37-degree angle. The plane from side to side is 5 meters long, 3 meters tall, 4 meters wide, and the weight of the block is 20 newtons. First of all, for 14, we just want to find the mass. We know that weight equals mg, which means mass equals weight divided by g. So let's take 20 and let's divide it by 9.8 to get the mass. So 20 divided by 9.8, we end up with a mass of, with significant digits, 2.0. So that's all you had to do for 14. But for 15, we want to find the normal force. So to find the normal force, we first have to go up to our picture, and let's draw in the weight as an arrow acting straight down. We're then going to take that weight, and we're going to divide it into a component perpendicular to the plane, and another component parallel to the plane. Remember that the normal force is the force that the surface pushes back up on the object. And in an inclined plane problem, the normal force is going to be equal but opposite to this perpendicular component of the weight. So to find that, we know that this blue line is the weight, which is 20 newtons. And we know that this angle right here is always going to be the same as this angle right here. So it's 37 degrees. So to find our green side here, our normal force side, we're going to use cosine. And we're going to say the cosine of 37 is equal to F perpendicular, the perpendicular component of our weight, all over the hypotenuse, which is 20 newtons. So if we solve that out, and we go to the cosine of 37 times 20, we end up with about 16 newtons. So the perpendicular component of our weight is 16 newtons into the plane, and our normal force is 16 newtons out of the plane or up from the plane. That's 15. Your next homework problem was number 25. So here's what 25 looks like. Another inclined plane problem. And in this one, we have a block of mass 5 kilograms on an inclined plane. The horizontal and vertical supports for the plane have lengths of 4 and 3 meters respectively. The coefficient of friction between the plane and the block is 0.3. The magnitude of force necessary to pull the block up the plane with a constant speed is most nearly what? So again, back to PowerPoint. Draw a plane. We've got a 5 kilogram block. We know this side is 3 meters and this side is 4 meters. We know there's a coefficient of friction, 0.3, and we know that our block is moving up the plane at a constant velocity. And we want to know how hard we have to pull on it to move it up at a constant velocity. Here's the thing. If it's moving at a constant velocity, that means the force that we're pulling with up has to be equal to any forces that are pulling down. And there are two forces that are pulling down. The parallel component of the weight is pulling that way, and also friction is retarding our movement by acting that way. So what we need to find is we need to find how much friction there is and how much the parallel component of the weight is. Really, before we can do either one of those, we need to know what this angle is. And since we know two sides of this triangle, we can find that. Let's just use tangent. Let's call this angle theta, and let's say that the tangent of theta is equal to opposite over adjacent, so 3 over 4. So let's go 3 divided by 4 and take the inverse tangent, and we get an angle of about 36.87. All right, now let's take our picture. Let's draw in our weight, going straight down. Let's break that weight into a perpendicular component and a parallel component, remembering that this angle right here is going to be 36.87 degrees, and that this right here is the weight. We don't know the weight, but we know the block is 5 kilograms, so let's go 5 times 9.8. The weight of our box is 49 newtons. So now if we break those into components, find F parallel and F perpendicular. We could use the sine to find F parallel. Sine of 36.87 equals F parallel over 49. And the cosine of 36.87 equals F perpendicular over 49. So let's calculate those out. And we end up with a parallel component of 29.4 newtons. And that's pushing down the plane. And our perpendicular component is 39.20. And that's pushing into the plane. That's F perpendicular. Like we said on the last problem, the perpendicular component is also the normal force. So if we want to find the coefficient of friction, we need to go to what I call the Klein equation. The problem told us that the coefficient of friction was 0.3. And remember that the perpendicular component is equal but opposite to the normal force. So we're going to plug in 39.20 right here. So let's go 39.20 times 0.3, and we end up with a force of friction of 11.76 newtons. That's acting down our plane. So we have this force acting down, and we also have this parallel component acting down. That's 29.4 newtons. If we want to pull the box up the plane, we have to pull with a force equal but opposite to the sum of these two forces. So let's go 11.76 plus 29.4. To move the box up the plane at a constant speed, we have to pull with a force of 41 and some change. The best answer, according to this sheet, would be 42 newtons. So our answer there is going to be B. All right, we also have a couple of free body diagram problems. And I'm just going to go through these by looking at the problems with you. So the next set of problems was 27, 28, and 29. So on 27, we have these pictures. And what we want to know on 27 is which figure best represents the free body diagram for the box if it's accelerating up the ramp. Well, if it's accelerating up the ramp, that means there has to be a net force acting up the ramp. The forces pulling up the ramp have to be bigger than the forces pushing down the ramp. And the only problem where that looks to be the case, where the forces up seem to be bigger than the forces down, E. We've got a pulling force, FP, that's way bigger than friction. That box is going to go up the ramp. 28. Which figure best represents the free body diagram for the box if it's at rest on the ramp? Well, if it's at rest, there can be no net force. No net force, at least up and down the ramp. And the only one where that seems to be the case is D. Notice we've got a frictional force acting up, but the parallel component of the weight seems to be about the same, equal to the frictional force. So those two are going to cancel out. So 28's answer is figure D. Also, figure 29, which figure best represents the free body diagram if it's sliding down at a constant speed? Well, again, if it's at a constant speed, there's no net force up and down the plane, and the only one where that's the case is also D. All right, our final problem, number 30. Two blocks are pushed along a horizontal surface by a force of 20 newtons to the right. Let's find that problem real quick. The force that the 2 kilogram block exerts on the 3 kilogram block is. Let's go to a PowerPoint. Work that one out real quick. So we've got our two boxes. This one's 3 kilograms, and this one's 2 kilograms. We're pushing this way with a force of 20 newtons. It's a frictionless surface. That means that this 20 newtons is not only our applied force, it's our net force. We know that F net equals MA, and we know that A equals F net over M. We have a net force of 20 newtons, and that 20 newtons is not just acting on the 3 kilogram box, it's also acting on the 2. It's acting on the system mass. So we're going to divide that by system mass, 5 kilograms. We get an acceleration of 4 meters per second squared. What we want to know, though, is how much force does the 2 kilogram block push back on the 3 kilogram block with? Well, here's first what we need to do. We need to calculate the net force acting on the 2 kilogram block. The net force on the 2 kilogram block is going to be its mass, 2 kilograms, times its acceleration, 4 meters per second squared. So the net force on that box is 8 newtons to the right. That's being applied on the 2 kilogram box by the 3 kilogram box. But according to Newton's second law, the 2 kilogram box, when it gets pushed on this way with 8 newtons, it's going to push the other way with 8 newtons. So our best answer for number 30 is 8 newtons to the left. And that's where we're going to stop. Hope that helps.